Hello, we are Adrian, Peter, Jonathan, Joseph, and Charlie, and we are Team 4. This is our final presentation about the analysis of the latch clamp. The latch clamp we chose is made up of 11 parts. All of them, except for the lever grip, are made out of stainless steel. The latch clamp is designed to hold objects together, such as barn doors, hatches, and mold closures. The entire device is controlled by the lever. When the lever is pushed by the user, it pulls on the U-bar, and the U-bar pulls on the latch hook. The base plates ground the lever subassembly in the latch hook. The U-bar locks into place once the lever is pushed all the way down to the end of its travel, which then makes the U-bar parallel to the ground. When the lever is lifted from its locked position, the tension in the system is released and the U-bar can be moved, which frees the latch hook. As mentioned previously, our latch clamp is made up of 11 different parts when fasteners are excluded, as you can see in the exploded view on the right. All individual parts, excluding the lever grip, are made of steel for strength and rigidity. The lever grip is made of rubber, so the lever itself is easier for the user to grip, hold, and control. The bill of materials, or BOM, is shown on the left and lists the part name, quantity in the latch clamp, material the part is made from, and the associated manufacturing processes. Almost all of the parts are either stamped or forged in our latch clamp, and the assembly processes are detailed later in the assembly sequence analysis.
The first key characteristic is the distance in the x-axis between the outside of the latch hook surface and the inside of the U-bar surface while the clamp is in the locked position. This KC is especially important because it allows the latching process to occur. If this distance is unconstrained, interference may occur between the U-bar and the latch hook when attempting to secure the latch. If this KC varies from its nominal value, there may be inadequate clearance on the left and right sides of the latch hook for successful latching. The second key characteristic measures the vertical distance in the y-axis between the front of the U-bar cylindrical axis and the surface of the arm base plate in the locked position. The U-bar rests parallel to the base plate in the locked position, so it needs to be elevated a minimum distance above the base plate to avoid interference. This figure illustrates the relationship between the KC and the latch clamp function. If KC2 deviates from its nominal value and does not achieve U-bar parallelism, the device will not be adequately locked. Additionally, if this KC is smaller than its nominal value, the fasteners connecting the fulcrum brackets to the base plate will interfere with the connecting rod, preventing the latch from closing. Datum flow chain analysis was completed on the latch clamp assembly and is illustrated here. Mates are labeled with solid lines with arrows, along with the respective degrees of freedom that they constrain. Key characteristics are labeled with double lines. KC1, a x-distance KC, is labeled in blue, as are the mates which deliver x-axis constraints. It should be noted that our assembly does not have a full delivery chain that can maintain the x-distance of KC1 from just the part constraints alone. This means our assembly requires a fixture to meet this KC, and is therefore a Type 2 assembly. KC2, a y-distance KC, is labeled in red, as are the mates which deliver y-axis constraints. Here it is important to note that there are multiple delivery chains which can fulfill this KC, making KC2 over-constrained.
Now that we have examined the current datum flow chain of each KC, it is necessary to list the assembly features that realize each mate in the datum flow chains and graphically explain how they constrain the labeled DOFs. The figures on the following slides depict each mate in the datum flow chain along with the rationale behind its labeled constrained DOFs and the portion of the datum flow chain to which it corresponds. We begin with the latch hook to the base plate hook. Two M5 by 12 bolts are used to secure these two parts together, preventing motion in all 6 DOFs. Next, we have the base plate hook to the base plate arm. The butt joint between these two parts prevents motion in the Z global coordinate frame, which is the left-right direction in the figure. We now have the base plate arm to both fulcrum bracket left and fulcrum bracket right. For both of these mates, two M5 by 12 bolts are used to secure these two parts together, preventing motion in all 6 DOFs. Next, there is fulcrum bracket left to fulcrum bracket right. The butt joint between these two parts prevents motion in the X global coordinate frame, which is the left-right direction in the figure. We now examine the fulcrum bracket right to lever arm right and fulcrum bracket left to lever arm left. For both of these mates, a butt joint between parts prevents motion in the X global coordinate frame, which is the left-right direction in the figure. Next is the fulcrum bracket right to lever pin and fulcrum bracket left to lever pin. Both of these mates permit translations and rotations in Y and Z and are constrained only in X, as there is a gap between the fulcrum brackets and the X dimension depicted in the figure to the left. The lever arm right to lever pin and lever arm left follow the same logic as the previous mate. Both of these mates permit translations and rotations in Y and Z and are constrained only in the X, as there is a gap between the fulcrum brackets and the X dimension depicted in the figure to the left. Next, the lever arm right to lever arm left are only constrained in the translational X DOF, which is depicted as the up-down direction in the figure to the left. For the lever arm right to connecting rod and lever arm left to connecting rod, both mates are able to rotate and translate in the X DOFs, as there is a gap in the X dimension between parts. However, Y and Z rotations and translations are constrained. From the connecting rod to the U-bar, all 6 DOFs are constrained, as there is a combination of a torque and a hex nut on each mate, along with the hole through which the U-bar is attached to the lever arms to constrain motion in the product state depicted. Finally, from the U-bar to the latch hook, the parts are able to rotate and translate in the X DOFs, depicted in the figure to the left. Translations and rotations in the Y and Z DOFs are constrained.
Now with part contact and mating analysis conducted, we can reapproach the DFC constraints. As Charlie mentioned, we are under-constrained in KC1, which is an X distance both at the base plate hook to base plate arm and lever arm to connecting rod liaisons. Fortunately, we are able to resolve this with a fixture, shown in red, making this a Type 2 assembly. How it works is the latch clamp base plates will be butt up against the raised edge of the fixture, which forces rigid contact in the X coordinates between the base plates. Then the flange, which extends upwards and then inwards, provides a fixed X distance between the connecting rod and lever arm left. The DFC is then showed on the right, modified with the fixture. Thanks to that fixture, we have proper KC1 constraint, but we are still over-constrained in KC2. This is due to having multiple delivery chains by nature of the symmetrical halves of this device, with 2 main chains between the right and left sides of the device, leading to 4 total delivery chains. Fortunately, this design has no KC conflict due to different coordinate directions for each KC, but a redesign is still considered because of the overconstraint of KC2. A redesigned solution is possible if we combine the left and right fulcrum bracket and left and right lever arms into unified parts, respectively. This will allow the same general assembly sequence to be taken, as well as no functional differences of the clamp. We then see proper constraint of KC2 with 1 delivery chain.
Finally, we discussed the manufacturing process by comparing 2 assembly sequences. This first sequence, deemed the ground-up approach, can be seen on the bottom of the slide and uses plates B and C as the ground or the fixtures along which the rest of the product is built. On the right side of the slide, we have the assembly tree, which shows again that these 2 parts serve as the basis for assembly. The pros of the sequence are that few fixtures are required and that the U-bar can be tightened during assembly. However, the main cons are that KCs are harder to deliver, KC2 in particular, and that this continuous assembly does not allow for any sub-assemblies, which makes testing difficult. Sequence 2 is a sub-assembly based approach, as can be seen again on the pictures at the bottom of the slide, where 3 sub-assemblies come together to create the final product. And again, on the right side of the slide here, we have the tree, which shows these different sub-assemblies coming together. The main pros of this sequence are that these sub-assemblies break up the manufacturing and allow for greater testing of the different components as they come together. This sequence is also more efficient at delivering KCs, particularly KC2, during assembly. However, this method or this sequence requires more fixtures, again due to the multiple sub-assemblies. And finally, we compare the 2 sequences along multiple criteria. Overall, we came to the conclusion that sequence 2 is optimal because these sub-assemblies allow for greater testing, as was mentioned, as well as better KC2 delivery. The one justification for sequence 1 would be that it requires less fixtures. However, overall, again, we came to the conclusion that sequence 2 would be more optimal in a real manufacturing setting.